Hi everyone, welcome back. Now we're going to proceed to Chapter 4, which is about insolation and temperature. We are going to spend this chapter talking about all of the wonderful things the sun does for us. He is our friend. Without the sun, there would be no life on planet Earth. So all of our energy comes into the planet as solar energy, and then is made into a variety of other types of energy, but it all begins with the sun. So all living things are influenced by temperature, right? Whether that is something that lives in the desert or something that lives in the Arctic, all living things are affected by temperature and have an ideal temperature range in which they can live. And human beings are part of this as well, right? We in San Diego could probably spend most of our time without some type of big protective gear on, and we do live in all parts of the planet, most parts of the planet, but we use a variety of tools in order to be able to do that. We also have a lot of adaptation to temperature extremes, right? So very often you'd go into the desert and you'd expect to see a lifeless landscape because there's very little water and such hot sun, but there's actually an abundance of life in the desert. It is just adapted to live there and conserve water in very, very specific ways. When we talk about biogeography for chapters 10 and 11, we will get more into those adaptations. And so all of this solar radiation coming in affects the soil and the bedrock. So we're going to talk about solar radiation and energy, but first we need to talk about what energy is. And this is going to be a very basic explanation of what energy is. Energy is what makes stuff move. It's described as the ability to do work. And so if we look at this very simple diagram here, potential energy, you have a circle or we'll say a ball that is balanced on top of a pyramid. That has a lot of potential energy, right? It has gravity that can pull down on it. If it's tipped over, it has the potential to do work. Kinetic energy is that actual moving energy. So once that ball moves, that energy that it is displacing by rolling down the side of that pyramid, that's the kinetic energy. And power is how we talk about how much energy is transferred over time, and we refer to this as watts. So when we talk about temperature and heat, we want to talk about the difference between temperature and heat because that's an important one. Temperature is the average kinetic energy of the molecules in a substance. Right? So when we use the term it's 70 degrees outside, we are describing the average kinetic energy of the molecules that are in the air around us. And so if we look at this pot of boiling water and this pot of boiling water, if they're both 212 degrees, they have the same temperature, right? Because it's an average of the kinetic energy. The bigger pot of water doesn't have more temperature. That differs from heat. Heat is energy that transfers from one substance to another because of a difference in surface temperature. So for example, if I have a cast iron pan on a fire and I grab the handle of that, that fire has transferred heat into that pan, and when I touch that pan, the laws of energy say, okay, your hand is much cooler than this pan is. I'm going to rapidly transfer heat I'm going to rapidly transfer energy, from one substance to another, from the pan to your hand, right? So heat is that energy that's being transferred from one substance to another. We measure temperature using 3 different systems. In the United States, we use Fahrenheit, where water boils at 212 degrees at sea level. Normal room temperature is around, just below 70 degrees, 68 degrees, and water freezes at 32 degrees, which these kind of seem like somewhat arbitrary numbers, right? So don't worry about the K one, that's Kelvin, which is not really used colloquially and we're not going to talk about in this class. We're also going to talk about Fahrenheit and Celsius. this map shows all of the countries in the world who use Fahrenheit. We are in a minority. The rest of the world uses Celsius, where water boils at 100 degrees and freezes at 0, which is pretty intuitive. But we are kind of stuck in this Fahrenheit system for now. But I will refer to both in this class at various times. But if you want to go from Celsius to Fahrenheit, a way to do that is if you take the temperature in Celsius, if you multiply it by 2 and then add 30, you'll get a roundabout answer. It's not perfect. So if you look here, 20 degrees Celsius, if you multiply that by 2, it's 40. If you add 30, that's 70, which is about what it is in Fahrenheit, which is a helpful thing if you're not really familiar with Celsius and you're traveling in other countries and they say, oh, it's going to be 27 degrees out today, and you're like, I have no idea what 27 degrees feels like or how I'm supposed to dress for that. So again, countries that use Celsius. Oh, and this map is also countries that have put a man on the moon. I forgot about my little joke in there. But we put a man on the moon, but we also still only use Fahrenheit. So solar energy is electromagnetic energy, right? The closer you get to the sun, the higher it is in intensity. The lower, the farther away you get, the more it's diffused and it's of lower intensity. But that solar energy coming from the sun is electromagnetic energy or electromagnetic radiation. And so there is a long spectrum of electromagnetic radiation that goes all the way from cosmic rays to long wave radios. Visible light is part of this spectrum. We can only see a very, very, very small amount of the amount of electromagnetic radiation that's out there. So all the way from cosmic rays, where you have the wavelengths of electromagnetic radiation are really, really close together, to the long radio waves where they're very, very far apart. The gamma rays, which apparently created the Hulk. But so we have a very, very short amount that we can see with our eyes. We use X-rays to diagnose medical conditions. Ultraviolet rays are the ones that will give us unfortunate sunburn if we don't protect ourselves, and the ozone protects us from a lot of this. Infrared radiation, and we'll talk about this, is what's re-radiated from the Earth. So very often satellite imagery will use infrared in order to map certain phenomena. So again, on this side you have shorter wavelengths, and on this side you have longer wavelengths. So different wavelengths interact with different kinds of matter in different ways. So some are transmitted, or they pass through something. Some are reflected, and some are absorbed. And absorbed radiation is usually then re-radiated back at a longer wavelength. And so, for example, if we put our hand through, zap it with some X-rays, it can transmit through a lot of this, which is how we get this nice picture of all of the bones in our hand. If we have a light bulb, this light bulb is throwing off a certain amount of radiation. Some of it is reflected from our hand. The part that is reflected is going to be that visible light spectrum, which allows us to see our hand. And some of it is actually going to be absorbed by our hand if we get close enough. We're going to feel some heat from that light bulb. You have to be pretty close. But some of that light will be absorbed by your hand. Some of it is going to be reflected off of it. And so when thinking about absorption and reflection, I'm going to use my dogs here. This is my dog, Millie, who's terribly cute. And this is my dog, Gertie. Millie really prefers to be inside on a hot day, and Gertie on a hot day wants to raid my garden and sit in the hot sun in the nice warm dirt. So this is a result of something called albedo. Albedo is the percentage of visible light that is reflected off of a surface, right? So Gertie, the color white is reflecting lots of that light. And so a lot of that radiation that's hitting her white fur is bouncing back off and showing up to our eyes as the color white. Millie is absorbing a lot of that radiation. For the same reason, if you are out on a hot sunny day and you're wearing a long sleeve black shirt, you will be much warmer than if you are wearing a long sleeve white shirt. So Gertie is my high albedo dog, which means she has a lot of reflection, and Millie is my low albedo dog. And so they will find very different places to hang out on a hot day. And so again, with albedo, higher albedo is lighter surfaces, less energy is absorbed, so there's less heating. It's mostly being reflected. So snow has really, really high albedo, which is why if you go skiing and it's really, really sunny outside, the snow can make your sunburn so much worse because it's reflecting a lot of that light right back at you. Low albedo is darker surfaces, more energy is absorbed, you get more heating, right? So the pavement on a hot summer day will get much, much hotter than the surrounding desert that's next to it over here, because it is going to absorb much more light. The greenhouse effect, which is a good thing, is what traps some of that heat near the surface of the planet and allows us to kind of live here happily. This is a good thing. I know the greenhouse effect is often referred to as this kind of negative thing when we're talking about climate change, but without any of the greenhouse effect, we wouldn't be able to be here. So shortwave radiation comes into the planet. It bounces off of the planet as infrared, as a longer wave. And some of it is trapped by our atmosphere, some of it escapes. So one of the problems that we'll talk about with global climate change is the fact that not enough is escaping. We have added too many greenhouse gases to our atmosphere, so more radiation is being trapped at the surface. So visible light transmits through the atmosphere. The surface absorbs some of that visible light, and the Earth re-radiates infrared light. That infrared is absorbed by greenhouse gases, and the atmosphere warms, right? Which, again, is a nice thing. It's also the same reason why that greenhouse effect of why you can't leave your dog in the car on a hot day, right? That visible light, that shortwave solar radiation is traveling into your car through the glass, but it cannot be effectively re-radiated back out, which is why if the average temperature in your car is only 70 degrees, it can quickly rise to 100 degrees if it's in the sun, because there's no escaping for that. So don't leave your dog in the car on a hot day. The next thing I'm going to talk about is conduction and convection, which are ways that heat is transferred. So conduction is the transfer of heat energy across a medium. And so here, these illustrations with the frying pan and whoever is grabbing this hot metal rod here are some pretty smart people, but basically if you take a hot metal rod and you stick it into fire, it's going to heat that hot metal rod, which will eventually reach your hand through conduction, and then your hand is going to feel that heat. These are the results from molecular collision, right? The molecules down here start moving really fast, and they move fast, and they move fast, and they keep bumping into each other, and next thing you know, it's hot all the way up here. Air is a really poor conductor. Metal is a really good conductor. This is why when we buy a down jacket in order to keep us warm, is because that air is such a poor conductor of heat that all of that space keeps your body heat from escaping to the outside, right? So air is a really poor conductor, metal is a really good one. That's the same reason as well too, on a really cold day, if you sit on a metal bench, the metal bench will feel colder than everything else. And it's not colder than everything else, it's the exact same temperature, but metal is such a good conductor of heat that as soon as you sit on it, that metal starts to just really effectively grab the heat from your body. Convection is a different way that heat moves. When we talk about in the next chapter, when we talk about how kind of air pressure and air moves, it does a lot of this through convection. It's heat transfer by the vertical circulation of fluid. Now, by fluid, I don't mean liquid. I mean things that can move freely, that are fluid. And these are generally water or air. And so if we look at here, we see there's a radiator, which are really common in Connecticut, in some older houses, and less common in California. But you have this radiator. It is kind of heating up this air, and it's forming this convection loop that is pushing this air around the room, right? Molecules move in tandem in big blobs of air, and it does this in water as well. And this forms a convection cell. We're going to talk a lot about convection cells in the next chapter. They're very important. The next thing we're going to talk about is adiabatic cooling and warming. We are going to talk about this a lot more later in the semester, but basically the idea of adiabatic cooling and warming says that if you have warm air rises, right? And so as this warm air rises, it will cool. It gets to expand. And the process of expansion cools the air. As cold air sinks, it condenses, and it compresses, and it warms. There's no heat being added to this. It's just the expansion and the compression. As you compress air, it warms. So when you're flying in an airplane, the air pressure outside is very, very low. It looks kind of like this, but it's also really, really cold. And so a lot of people would think, well, I'm flying in an airplane. The airplane must have heaters in order to heat the inside of the airplane. And they don't. They are taking air from the outside, compressing it, and that is creating warmth. And we'll talk about adiabatic cooling again later in the semester. But what you should know about adiabatic cooling and warming is basically as warm air rises, it's going to cool through the expansion process, and as cool air sinks, it's going to warm through the compression process. Insolation is just a way to describe the solar energy per surface area, which is watts per square meters. So it's just how we measure and describe how much solar energy any given part of the globe is getting at any given time. So if we look here, this is the annual mean of net solar radiation or insolation. You could see way more at the equator, less near the poles. And so what you should know, and you don't have to know all parts of this illustration, but basically Earth has a radiation budget, right? It has, it's like a banking system. A certain amount of solar radiation comes in, and it is used up in a variety of ways, but it all is going to equal out. So you have 100 units here, and then minus 100 units here, right? Eventually, it's all going to be re-radiated out to have equal. Because otherwise, if we were slowly just gaining more and more solar radiation, our planet would just keep heating up and keep heating up and keep heating up. We have variations in insolation depending on the angle of incidence. And what that means, we talked about this with the angle of the sun being in the sky previously, but the angle of incidence at the equator right here is 90 degrees. The angle of incidence at the poles right here is 10 degrees. So the amount of insolation that's coming in is being dispersed along a broader area. We also vary this because of atmospheric obstructions. So if it's a very cloudy day, we're obviously not getting as much solar radiation as if there were clear skies. And also day length. On shorter days in the winter, we are receiving less solar radiation than we are on long summer days. And we also have seasonal variations in insolation. We talked about the reasons for the seasons in previous chapters, right? But generally speaking, so here is December average daily insolation, and here is June, and the northern hemisphere here is having winter, so it has shorter days, getting less sunshine, getting less solar radiation, as opposed to in the summer getting a lot more.